Hi, everyone. This is the lecture for April 28th for Physics 112 and for April 29th for Physics 102. It's the last video that I'm going to do that's going to present new material, and it's going to be all on ray optics. I am, of course, still going to have videos up for the other classes, but they're going to be dedicated to just review for the final. Okay, and watch your emails because there'll be a slightly different format. I'm going to be doing live streams so that I could look at the chat and see if people have any questions. And I'll basically have a series of problems. I'll just do the problems and then pause and see if someone has questions and address those questions a little bit more interactively. Okay. And when will those live streams happen? Well, I'll specify. They'll happen during your regular class times, but I'll specify that during the or in the emails that I send out. Okay, so let's begin our study of ray optics. Where is the material? Well, if you're Physics 102, go to our Moodle site, and at the very bottom of the page, it's the April 29th notes in PDF format. And of course, if you're Physics 112, go to the Physics 112 site, and at the very bottom, it's the April 28th notes. Okay, so they're identical. These notes are identical for both classes. There's no calculus involved in any of this. Okay, so all right, ray optics. Why is it called ray optics? First of all, let me tell you a little bit about optics in general. Optics, if you want to broaden it right up, is really the dynamics of waves, which we studied earlier. Okay, it's how waves propagate and so on. Okay, and in particular, it's usually talking about light. Okay, but it could be any waves. All right, although we will be talking about mostly visible light. Okay, ray optics, however, is sort of a subset of all of optics, and it's just basically looking at optics which can be reduced to just the tracing out of the rays that a wave etches out as it propagates. Okay, so let me begin by reminding you what a wave is and what rays are for a wave. Okay, so if you see in my diagram here, we've got a wave, and you can think of this as like looking down and see a water tank or something like that. And so you have alternating crests and troughs, and you can see here the solid vertical lines. Those are crests, and I've got them labeled here as crests. And the vertical dashed lines, those are troughs, and so you've got crest, trough, crest, trough, crest, trough, like that, forming a wave. Of course, this is just a snapshot in time. If you were to actually watch this as a movie, the wave would propagate, and I'm showing you here that the wave is propagating to the right with some velocity v, like that. And you could define the wave as being a line, okay, which is perpendicular to the wavefronts, perpendicular to the crests and troughs, and pointing in the direction of the propagation of the wave. Okay, and so in this case, the ray would be pointing to the right, like that. All right. Now, I started off by saying that sometimes you only have to worry about tracing out the rays for your optics. And so when is that the case? Okay, when can you reduce your full optics, your full wave optics, to just ray optics? Well, if you remember, we went through 4 phenomena that waves exhibit. Okay, they exhibit lots of phenomena, but four in particular. One of them is reflection. The other one was refraction, and the other one was diffraction, and the other one was interference. Okay, now for diffraction, and diffraction was the bending of waves around corners, and for interference, and that's when you had two sources of waves, and the crests and troughs from one source would meet up with the crests and troughs from another source, forming bigger crests or bigger troughs, or annihilating one another, as the case may be. Okay, so diffraction and interference, those occurred when your optical devices, like holes or barriers or whatever, were approximately the size of the wavelength. Okay, so once again, diffraction and interference really are only of issue if you're talking about your optical devices being about the size of the wavelength. Okay, now if we're talking about visible light is it's basically the rainbow from violet to red. So the wavelengths of visible light are between 380 nanometers. Remember, nano is 10 to the minus 9, so that's billionths of a meter. So 380 billionths of a meter to 740 nanometers. Okay, so 380 to 740 nanometers. That's pretty small. Okay, and so as long as your optical devices are much bigger than that, you really don't have to worry about diffraction and interference. It's not that they don't occur, it's just that they're negligibly small compared to everything else that's going on, okay? And so when we're talking about things like eyeglasses, okay, eyeglasses are, I mean, you know, they're several centimeters in size, so they're way bigger than the wavelength of light, okay? And so for that reason, you don't have to worry about the diffraction and interference. All you really have to worry about is reflection and refraction. Okay, and just to remind you, what is reflection? Well, that's easy. You know, when a wave meets a surface that it can bounce off of that doesn't absorb the wave, it just reflects, and it reflects such that the incident angle is equal to the reflected angle. And refraction is when a wave travels from one medium to another, and the rays bend. Okay, and that was Snell's law. We'll see that in just a second. All right. So we're basically going to study array optics, and in ray optics, we really only have to worry about reflection and refraction. All right, so the two optical devices that we can make using reflection and refraction are, for reflection, a mirror, and for refraction, a lens. Okay, so we're going to study lenses in more detail, because they're a little bit more interesting, but let me just introduce the mirrors. Okay, so mirrors, like I just said, they basically operate by reflection. Okay, and you know, the light will come in and it'll impinge on the mirror, and the light will bounce off, the rays will bounce off, and they'll bounce off such that the incident angle will equal the reflected angle, okay, as they bounce off, right? Well, there's, I mean, I guess you could have many shapes to your mirror, but there are three shapes that we're going to look at. One, well, think about, well, one of them is uninteresting. There's a concave mirror, all right, and there's a convex mirror. They're both kind of got a rounded shape to them. Okay, and there's also a flat mirror. Okay, now flat mirrors, there's really not much to do with them. That's the mirror that you look in every morning. You know, it's like your bathroom mirror or whatever. But concave and convex mirrors, they have some more interesting optical properties. All right, so let's look at those two. So let's look at the concave mirror first. Okay, so the word concave, you'll see that with lenses too. It means kind of caved in. All right, so something is caved in like this. Okay, so you can see here the reflective surface is on the, I guess, on our right-hand side, and the non-reflective is the back of the mirror is on the left. Okay, you can see the non-reflective surface. I put some little etches in there. All right, and this mirror here, concave. It's not only concave, but I also gave it a shape. It's a semicircle. So it's like a little segment of a circle. All right, and that semicircle there is centered. Like if you were to extend all the way around here, if you were to extend the circular portion of the mirror all the way around, it would be centered such that the center of the circle would be this point C here, like that. Okay, and so C is the center of the curvature, the center of the circle of which that mirror is made. All right, so what would rays do if they came in and impinged on this mirror? Well, they would reflect, but how would they reflect? So let's take a look at rays that are coming in parallel to what's called the axis of the mirror here. So this is the kind of the middle of the mirror. So we got this ray coming in. It's coming in parallel to this axis here, and it impinges on the mirror right there. Okay, and remember, incident angle is equal to the reflected angle. And I didn't draw the normal there or anything like that because I didn't want to mess up the diagram too much. But you can imagine that this incident angle is equal to the reflected angle there. And here's the outgoing ray, and the outgoing ray passes like that, and it passes through this point F. Not through C, not the center of the curvature, but through this point F, okay? And so that's one ray coming in. So let's just trace that ray again. It comes in, hits the mirror, and then bounces off, and it bounces off such that it passes through that focal point. Well, what about another ray that comes in parallel? I mean, there's an infinity of rays coming in parallel. We don't have to trace them all. So let's trace another ray that comes in parallel. Here it is here. Okay, so here's another ray coming in parallel. It impinges on the mirror. It reflects, and it also bounces and passes through that focal point too. Okay, I'm sorry, I didn't quite draw this as a straight line, but of course all these rays should be straight lines here like that. Okay, so this ray comes in, hits the mirror, bounces, and it passes through a focal point on the way back out. Okay, and so this focal point is kind of a point through which all rays that come in parallel, when they bounce, they will all pass through that focal point. All right, so that's maybe the name focal because that's where all the rays will converge through that point there. Okay, now if you make use of the fact that the incident angle is equal to the reflected angle, and you go through the geometry, which I'm not going to do, you can actually show that the focal length here, that is the distance, the focal length being the distance from the mirror to that point F, to the focal point, that distance is actually equal to half of the radius. Okay, so if here's the center of the curvature C. If you were to measure the distance from C to the mirror itself, that would be the radius of the circle. Remember, the mirror is semicircular. Semicircular meaning it's just a portion of a circle. Okay, so the distance from C to the mirror would be some distance r, and the focal point is half of r. Okay, and that can be shown through some simple geometry. All right. So there's the story with the concave mirror. You can similarly make a convex mirror. Okay, so what's a convex mirror? It's in a sense got the same shape, being semicircular as the concave mirror, but we're going to switch the opaque and the shiny side. Okay, so the shiny side is on the outside over here, on this side over here, and the opaque side is over here, and here's the center of curvature right there, and the focal point is there. Okay. And once again, if you do the geometry properly and you make you impose the law that the incident angle is equal to the reflected angle, you're going to find that these rays come in, they impinge on the mirror, and they bounce out. But this time, they don't bounce out and pass through the focal point. They bounce out as if they were traveling away from a focal point or diverging away from a focal point. So here's this focal point. It's now behind the mirror. Here's a ray coming in, and it bounces away, and it bounces away such that it diverges away from that focal point like that. Okay, so this dashed line back here, that's just a construction line to show you that this ray is diverging away from that focal point. Okay, and all the rays coming in parallel will do that. I just drew a second one, but all infinity of them will do that. So here's another ray that comes in, it impinges on the mirror, and it bounces out, and it bounces out such that it is diverging away from that focal point. All rays coming in parallel bounce out, and they all diverge away from that focal point. Okay, and once again, that focal point is half the radius of the mirror's curvature. Okay, so there we go. There's the convex and the concave mirror. We're not going to do much more with them because we're going to look at the concave and convex lens. And the reason we really don't have to study these anymore is because everything that we do with the concave mirror, it's just like the convex lens. Okay, they are both considered converging optical devices, and you'll see that when we do the convex lens. And so, to study the convex lens or to study the concave mirror is really to study the same kind of optical device with just some small details of difference, and they're not that interesting. So we'll concentrate on the lenses. So concave mirrors act like convex lenses, and conversely, convex mirrors act like concave lenses. Okay, so to study the convex and concave lenses is basically to study the convex and concave mirrors anyhow. All right, so let's turn to the lenses and look at those in detail. Okay, now there's one subtle thing that's different about the mirrors and the lenses. Okay, remember the mirrors, they're optical devices based on reflection, the property that waves exhibit, which is reflection. Okay, whereas the lenses are based on refraction. Okay, and refraction is a little bit different than reflection. Okay, so remember that reflection occurs because of Snell's law. Okay, so there we go. We've got Snell's law right there. All right, and basically what it says is if you have two medias, index of refraction n1 and n2 like that. All right, and you've got an angle in medium n1 sine theta 1, and you got an angle in medium 2 sine theta 2 like that, then it's related by this formula here. We actually won't need to work with that formula directly, all right, but we can just refer to it. All right, so what we have here is a ray that's going to come in. I have this glass here, and it's not just a flat plane of glass, it's basically just a kind of a triangular shaped plane of glass like that. And if we make use of Snell's law at this first point here, which is an interface between air and glass like that, okay, the ray will bend like that towards the normal. Remember, when a ray goes from a low end to a higher end, it'll bend towards the normal like that. And then it'll do it again when it exits the glass and goes into the air, and it'll also bend away from the normal this time. And so basically you get this double bending. Once when the ray enters from the air to the glass, and again when it passes from the glass back into the air. Okay, and so if you were to follow this ray and it weren't bent at all, it would follow along this dashed line here like that, and that dashed line there like that, okay, is at an angle, and I just called it phi, to the actual direction of the ray. And so you could see that by shaping your glass in this kind of triangular form like that, you've basically effectively been able to bend the ray by an angle phi like that. And this phi here, we're not going to calculate it, but you could calculate it. If you went through the details and you said, okay, what's the angle of incidence here? And what's the refracted angle there? Okay, and you could solve that, of course, using Snell's law here. And then once you get that, you do it again, and you look at the incident angle here at the other interface, and then the refracted at the other face, you'll get that angle there. And putting both of those angles together, you would get this angle phi. Okay, it would be difficult. It would just be tedious. You would have to apply, you apply it at two interfaces, and you'd have to apply Snell's law at two interfaces, and you would have to worry about the details of, like, what angle, what's the angle here and what's the angle there of the glass in the air and so on. Okay, so we won't have to go through those details. All we have to know, keep in mind, is that basically Snell's law does lead to this refraction, double refraction, sorry, and leading to this angle phi here. All right. So great. It seems, well, then, all you have to do is just design your glass in such a way as to bend the angle, bend the rays by some angle, and then you could get the same behavior as a mirror, but not exactly, and here's why. Snell's law here, the index of refractions, they have a slight dependency on the wavelength of the light. Okay, so I didn't mention this during, when we were looking at waves, but if you do a proper analysis of, Snell's law in terms of like the underlying wave equations that give rise to it, you would find that the index of refraction, N1 and N2, actually do have a dependence on the wavelength of the light. Okay, and that means that red light actually doesn't bend as much as violet light. Okay, and so that leads us to a prism. All right, and maybe you've played with prisms before. Basically, it's just a triangular piece of glass, and it makes use of the fact that N, the index of refraction of the glass, depends on lambda, okay, to break up the light into its component colors. All right, and so here I've drawn a prism, and I don't have colors, but basically, you can just imagine here you've got white light coming in here, and when the white light impinges on the glass, the red light, so white light is made up of all the colors, okay, of the rainbow. The red light won't bend as much, and so it's going to travel along this upper edge here like that, and then it'll bend again, but again, it won't bend that much, and so this upper edge here will give you the red end of the spectrum for this white light. Okay, the violet light, which is at the other end of the spectrum, will bend the most, and so you can see it here bending more than the red did, and then even when it exits, it bends even more. Okay, and so the bottom edge here, that's going to be the violet, and in between you're going to have all the other wavelengths of light, in other words, all the different frequencies from red to violet, and that gives you the rainbow. Okay, so you're going to have red, orange, yellow, green, blue, violet, and or indigo and violet. Okay, so there you go. That's how rainbows work. So, when you see a rainbow in the sky, you might wonder what's happening there. Why are you seeing a rainbow, in the clouds? And the answer is all the little droplets of water, which are kind of circular in shape, they're all acting like this prism. Okay, and they're all splitting up the light, and that causes the rainbow effect. Okay, so so there you go. Now, this is important because this does not happen with mirrors, because in mirrors, the incident angle equals the reflected angle. Doesn't matter what lambda is. Okay, doesn't matter what lambda is. So, but for refraction, it does. And that means that I'm going to be making an assumption about my lenses that I'm going to be doing later to avoid the complication that the refraction is really wavelength dependent. We're going to be working with thin lenses that it's always a problem, but it's not as much of a problem. In other words, we're just going to ignore this problem. But I want to mention that it is there, and like eyeglasses, I mean, they have to take that into consideration. Otherwise, if you just had simple lenses for eyeglasses and they went ahead and they broke up light into the different colors, then you would see kind of like rainbow hazes everywhere, and we don't want to see that, okay, with our eyeglasses. All right, so there's the story with refraction with real light, which is white. Okay. Now, I do want to say a little bit about where light comes from. Okay, like what is the source of light? So one source of light, you can say white light, like this. Is where does this white light come from? Well, I mean, the most obvious source is the sun. Okay, and another source is an incandescent light bulb. And these sources of light are what are known as black body radiators. Okay, it's known as black body radiation. Okay, and that seems like a very strange name for a source of light, because you don't think of black as emitting light. You think of white as emitting light. But the reason they're called black body radiation is because the material itself is actually an absorber of light, and what's causing the light is heat. Okay, this is actually light as a form of heat. Okay, now how that works is a part of modern physics, and it's beyond the scope of this course. But I think everyone's experienced this, where when you see something that's burning, the hotter it is, the more it glows a brighter and brighter red. And if you keep heating it up, eventually it'll start to glow white hot. Okay, and that's exactly what the sun is. The surface of the sun, at least, is basically just at a temperature somewhere around 6,000 degrees Kelvin, and that temperature corresponds to white light. Okay, so this is known as black body radiation, and again, it's just because the surface of the sun, if it were cool, would be opaque. It would not be it would not be transparent to light. Okay, and it's the heat of the surface of the sun which is causing it to glow at that particular temperature that is white light. Okay, now with white light, that is light from black body radiation, if you split its spectrum up, you would see that every single color in the rainbow is there. Okay, however, there's another source of light, and that is light that comes from basically just exciting atoms. Okay, individual atoms, and you could do this by just passing electricity through them. This is like a neon sign. Okay, so if you've ever seen like a neon sign or a helium neon sign, you can see these signs, and they glow. Okay, they usually make writing out of them, and they'll glow. They'll glow at certain colors, and you can see that they're kind of like, some like neon signs are kind of orangish in colors and so on. And then there's others that are green that are made out of krypton and so on. And that's another source of light, and that's a source of light that comes from not the heat, but from the electrons within the atoms. Okay, and so I thought it'd be important to say, like we have one source of light which gives us white light, which is the black body radiation, and another source of light which gives us particular colors. Okay. And let's take a look at the hydrogen atom, because that's the easiest one to understand what's happening there. For all these atoms that are giving off light, hydrogen or otherwise, only certain colors are allowed. So if you were pass light from a hydrogen, or say light from a neon sign or whatever, you pass it through a prism, you wouldn't get the full colors of the rainbow. You would only get certain discrete colors. Okay, and you wonder, why is that? Why would you only see certain discrete colors if you're passing, if your source of light is, say, glowing helium or glowing neon or something like that? Okay, so let's look at hydrogen, because hydrogen is the easiest one to understand. Okay, so you might have studied this in your chemistry courses. Okay, but the electrons, they orbit the nucleus, orbiting quotes. Okay, they orbit the nucleus, but they're not allowed any old orbit. They're only allowed certain orbits that are called shells. Okay, and so we can actually take a look at that just on the Wikipedia page. And so what you're seeing here, whoops, oh, I lost it. Hold on. I'm sorry, guys. I'm bouncing around a bit. Okay, so there we go. It's right below my picture here. What we're seeing here is that little red dot is like the nucleus of the atom, and then you can see n equals 1. That would be like the first shell, and the electron could be in n equals 1, or the electron could be orbiting in n equals 2, or it could be orbiting at n equals 3, or n equals 4, n equals 5, n equals 6, and so on. Okay, it can't orbit in the middle. It can't be orbiting at 1.5. Okay, or it can't be orbiting at 2.3 or something like that. It can only orbit at these discrete values. And the light that you see coming from the hydrogen atom is when the electron makes a transition from one of the shells to another shell. So this like n equals 6 shell, that's a high energy shell. It's a very big orbit. Okay, and when the electron jumps from this shell, gives up all of that energy, and it goes down to the lower shell, it gives off a little bundle of light called a photon, and that photon is of a particular color, okay? And so with the hydrogen atom, there's a whole bunch of different series, okay? So this is the Lyman series, and there's the Balmer series, okay? This is the Paschen series, like that. And so these are all different colors. Two of the series that you see here, they're not visible. Only the Balmer series is visible. And if you take the light that comes off of a hydrogen atom that's been excited by just passing high voltage electricity through it, you're going to see a spectrum which looks like this. Whoops, let me move it down. Oh, I can't move it down. All right, let me move move it down like this, okay? So you see a spectrum that looks like this, okay? So what's the spectrum? Well, it would be the full rainbow, all right, if this were white light, but it isn't. It's light coming off of hydrogen. And so you only see these discrete colors. You'll see this red, and then you'll see this light blue, and then a darker blue, and then heading into the violet like that, okay? And so each of those discrete colors, they're basically coming from the different transitions between the different shells like that, okay? And so you've got two different ways that you can get light, at least. There's probably other ways too, but at least two different sources of light. This black body radiation, which will give you the full rainbow, all colors, or light that's coming from, glowing atoms, okay? And glowing atoms just means that atoms where the electrons are jumping between the shells, and that'll give you only discrete colors, okay? Usually referred to as a spectrum, okay? So the Balmer series is the one that's visible for the hydrogen atom, and it forms those colors that you saw earlier. Well, let me give you a little bit of insight into what's going on there in terms of these shells, okay? And so for the hydrogen atom, like, you have this transition from n equals 3 to n equals 2, and that transition is the 656 nanometers. That's that red line that you saw, okay? You could also have a transition from n equals 4, which is a little bit further out, down to n equals 2, and that's 486, and that's a light blue, and then, there's the other ones that you saw in there, and each one is heading more and more into the purple, okay, or the violet is probably a better name for it, okay? Now, why? Why are there only discrete transitions, okay? And why do you only get these discrete colors? Like, why can't you have n equals 1.5 or n equals 2.3? Why is the electron only at these discrete orbits? And the answer is, we actually know this. It's standing waves, okay? Remember the standing waves, how they could only form, like if you tie a string down at two ends, it could only form certain shape waves. And so you had one with like one bubble in the middle, one antinode, and that was n equals 1. And then you had another shape wave which had two bubbles, okay, two antinodes, and that was n equals 2, and you could have n equals 3 and n equals 4. And so you only had these discrete frequencies at which the string could vibrate. That's actually what the electrons are doing when they're in an atom, okay? They're basically, these shells are basically different standing waves in which the atom which the electron can form inside the atom, okay? Now, that may seem strange because you might think of an electron not as a wave, but as a little particle that's orbiting in there. But in quantum mechanics, which is a deeper mechanics that, of course, we're not studying in this course, the electrons are more like shells, okay? So I thought it was kind of important to tell you this because you want to know something about the light that you're dealing with, okay? And so you've got this white light, which is the whole rainbow, and then light that's coming from glowing atoms, and the glowing atoms will only have discrete colors. If you take a look at the fluorescent lights in any, in any room, not incandescent. Incandescent would be is black body, it's the full spectrum. But you take a look at the fluorescent lights. The fluorescent lights, I forget what's in there, and I think there's some mercury in there and some other things. And you take a look at them using a prism, and you'll only see discrete colors. Okay, you won't see a full rainbow. That was kind of interesting. Okay, all right, let's get back to the ray diagrams that we're going to be drawing. And let's start off with the convex lens, and let's do the ray diagram, all right? And so I already mentioned this. We're only going to look at what are called thin lenses, and that means that the focal point is going to be simple, okay? It's not going to be a smeared out focal point. With the different colors, because they all have different index of refractions, they would all have different focal points, okay? Well, we're going to assume that all the light of any color is all going to pass through the same focal point. So there's going to be a simple focal point, not a smeared out focal point. Otherwise, the optics becomes much more difficult, okay? And a convex lens, the lens, that means that the lens is thicker in the middle and thinner at the edges. You can make that by making it curved on both sides, okay, so curved in the front or the back. Or another way you can make a convex lens, you can have one side which is flat and just have a curvature on the other side. But the important thing is that the edges are thin and the middle is thick, okay? For the concave, it'll be the other way around, all right? And all rays that pass through these convex lenses, they'll converge. You'll see that in a minute, okay? So they're going to be converging rays, and they'll converge through, well, you'll see that in a second. They'll be converging, so sometimes these are called converging lenses, right? And they act, the convex lens acts just like the concave mirror in terms of converging the rays. All right. Another name that you might have heard is, or that you probably know this by, is my magnifying glass. Magnifying glasses are convex lenses. All right. Now, for the convex lens, there's two different types of images that are formed. You'll see that in a minute. And so we're going to study two different situations. One situation is where we put an object further from the lens than the focal point. Okay, so this lens is going to have a focal point, and we're going to put an object and say what kind of image is formed by this object. One case is where you put the object further from the lens than the focal point and ask what kind of image is formed. Another situation is you put the object closer to the lens than the focal point and you ask what kind of image is formed. Okay, so there's actually two discrete cases that come up here. Not for the concave lens, that'll be, oh, there's only one case there, but for the convex lens, there's two types of situations that you can get into. One is where the object is further from the focal point, and the other one is where it's closer to the lens than the focal point. Okay, so let's start off with a little diagram which defines, a diagram which defines for you some quantities, some measurements, okay? So the first thing is, let me move that up a bit more. Okay, the first thing is this symbol right here, which is like a line with an arrow on the top and the bottom. That's a simple symbol for drawing a convex lens, okay? I mean, you can draw it as, you know, like kind of that shape there, but it gets kind of annoying to draw that for these diagrams, these ray diagrams. And so the symbol that's usually used for lenses, for convex lenses, is a straight line, and you just put these arrows there like that, okay? And now we're going to put an object, and here's the object here. The object I'm going to denote as an arrow, which is pointing upright like that. All right, and there's going to be an image formed. All right, and you'll see how that image gets formed later. But this is just for defining, you know, the distances between things. The image is going to be formed somewhere over here. Okay, the image could either be upright, or in this case, you're seeing it here, it's inverted. Okay, so you can see it's an arrow which is pointing down, so it's inverted. All right, and this line in the middle that goes right through the middle of the lens, we'll call that the axis, okay? So what quantities can you measure here? Well, the two dots here, those are the focal points, okay? And the focal points are a distance f from the lens, like that. Okay, so there's f on the one side and f on the other side. So there's two focal points because you can pass the light either way, okay? And if you were to pass the light one way, it would converge and pass through that focal point. Or if you pass the light the other way, it would converge and pass through that focal point. Okay? And so there's these two focal points, and they both are at a distance f. It's the same f on both sides because this is a simple lens. And also it's one focal point. It isn't a different focal point for every lambda because, again, this is a thin lens, and we're just going to keep it simple. Okay? Now, this DO, that's going to be the distance of the object to the lens, okay? And you can see that DO here is bigger than F, so this is the case where the distance from the object to the lens is bigger than the focal length, all right? And over here you have DI. DI is the distance from the lens to the image, okay? And there's two other quantities I've got drawn in here. HO, that's the height of the object, and HI is the height of the lens, okay? So I just drew this diagram to define those distances. I didn't want to, because I didn't want to just superimpose a bunch of diagrams on top of one another and make them too busy. But this defines all of those different lengths there. Okay, so I didn't even write them all down there, but the most important one is DO, the distance of the from the object to the lens. DI, the distance from the image to the lens, and F, the distance from the focal point to the lens. Okay, all right. Now, what we're going to do is we're going to do this thing called ray tracing. Okay, and so remember, rays are just like the direction in which waves propagate. And we have this object, and I've drawn it right here. I've just drawn the object, which is we can draw as an arrow. All right. Some of these diagrams you might see like the object drawn as a candle or whatever, but we're going to make this abstract. It's just an arrow like that. And every point on that object is actually emitting an infinity of rays in all directions. Every single point. So the base here and that point there and that point there, every single point. But we're not going to trace all of those because then it would get really messy. We're just going to trace the rays that are leaving the tip of the object. Okay, so there's these rays that are leaving the tip of the object. And even there's an infinity of rays, which is what I tried to draw here. All of these rays leaving the tip of the object, they're all traveling in different directions, okay? So what's happening is the object is being, illuminated by white light, okay? And the light reflects off of the object, and it just reflects in all different directions, okay? And so you can see here the rays traveling in all different directions. We're going to follow the fate of each one of those rays and see what happens to them, okay? Well, some of the rays are going to be boring because they're just going to go off in some direction, and they won't even hit the lens. Okay, and so we're not interested in those rays, all right? But some of the rays are going to hit the lens, and then the lens is going to bend them, and it's going to bend them because it's a converging lens. It's going to bend them in such a way as to converge them towards an image, okay? And so here's our first ray diagram, all right? So what do we have here? Well, this is the same diagram as the previous one, but I took out all the measurements of the distances so that, it wasn't too cluttered, okay? So what we have here, this O, that's the object, okay? So you can see here my arrow, that's the object, okay? Here's F2 and F1. Now, I call them F1 and F2 just so I could refer to them more easily below, but they're the same distance from the two focal points, but both the same distance from the lens. Okay, so the distance from F2 to the lens and the distance from F1 to the lens, that's the same. Okay, and an image is going to be formed, and here's the image over here. It's actually this upside down image, upside down arrow, okay, which I called I, and there's an axis, and then there's the lens. Okay, out of the infinity of rays that are leaving the tip of that object there, all right, we're going to trace 3 of them. You only need 2 to see where the image is formed, but there's 3 that we can trace. And I want to go through all 3 of them because in some ray diagrams, it's easier to draw one set, and another set of 8 ray diagrams, it's easier to draw a different set, okay? And so let's take a look at them, all right? So the first one, all right, number 1 here like that, you can see it there. I'm tracing it kind of backwards there, okay? That's number 1 there like that. So number 1 leaves the tip of the arrow, all right, and it travels parallel to the axis. It travels parallel to the axis until it hits the lens, okay? So you remember in my concave mirror, all parallel rays, they went through the focal point? For the convex lens, all rays that come in parallel, they're going to be bent such that they travel through that focal point, okay? So let me say that again. All rays that travel parallel to the axis, when they hit that convex lens, they're going to be bent such that they pass through that focal point, F1, okay? Well, we don't have to trace all, a bunch of parallel rays there. We just want to follow that one parallel ray that leaves the tip of the arrow, travels parallel to the axis until you hit the lens, and then gets bent through the focal point and travels out here like that. That's ray number 1, okay? Now, if you just drew ray number 1, you wouldn't know where the image is formed, okay? So you're not seeing me draw this thing dynamically, all right? But, you would draw ray number 1 first, and you would just have this line here and that line there, and you wouldn't know that where the image is yet. Okay? Now, there's ray number 2, okay? And this is that ray right there. Let me trace it backwards. So this is number 2 here, tracing it backwards, tracing it backwards, tracing it backwards. Rays can be turned around on themselves. So a ray that comes in parallel bends and goes out through a focal point. Conversely, a ray that passes through a focal point gets bent and travels out parallel. All right, let me say that again. Ray that comes in parallel bends and travels through a focal point. A ray that travels through a focal point bends and goes out parallel. Okay? And so now we can start from the tip of the arrow, and out of all those infinity of rays, we'll pick that one ray that leaves the tip of the arrow here, passes through F2, and impinges on the lens. That ray gets bent by the converging nature of the lens such that it goes out parallel. All right. Now, if you drew ray 1 and you drew ray 2, you would see that they converge right there at that point. And that's where the image gets formed. Okay? And so you would draw a little arrow there like that. And that tip there of the image corresponds to the tip there of the object. All right? So you only need 2 rays. You can draw out, coming in parallel and then going out through F1, or passing through F2 and then going out parallel, they would meet there, and great, you've got an image. Okay, so where the rays converge, that's where the image gets formed. I did draw this third ray because it's going to be useful in a minute to draw this third ray. Because of the geometry of the lens, which I didn't go through the details, okay, and applying Snell's law to the geometry of lens, a ray which passes right through the middle of the lens. In the middle of the lens is that point of the lens which is right on its axis. So you can see it right there. A ray which passes through that point doesn't get bent at all. That might seem strange to you. Go, why does that happen? And that's because of just the geometry. You know, at this point in the lens, the lens is as close to being just like a flat plane of glass. Okay, and so as a result, there's no net bending of the ray. Okay, and so you could just take that ray that starts from the tip of the arrow, passes through the middle of the lens, doesn't bend. And you could see that if you were to extend that ray, I did this with a ruler, so you can see the lines are nice and straight. The ray that leaves that tip, passes through the middle, also converges at the same point to form the image. Okay, so you've got rays 1, 2, and 3. They'll all come together and they all converge at that point right there. Okay, now our last lab in the course would have actually been to play with, you know, lenses and so on, and you would form this image in the lab, okay, using what's called an optical bench and lenses and so on. If you form this and you don't have a screen there or anything like that, you wouldn't see the image. If you look through the lens, you wouldn't see the image. In order to form this image, what you have to do is you have to put a screen right here where the image is formed. Now you could put the screen over here. You could put the screen over there. You wouldn't quite see the image. You would see a blur. And then you can move the screen back and forth until you get right to where the image should form. And that's where you see a sharp image formed onto a screen. Okay? And so in this case, which is the case where the object is further from the lens than the focal point, in other words, DO is bigger than F, the rays, when they pass through the lens, they'll actually converge to form the image, okay? And in order to see that image, you can't just look at it. It won't just form there in empty space. You got to put a screen there, a white screen, and the image will focus then onto the screen, okay? By the way, if you want to know what kind of real-world examples you have of this, that's the human eye. The human eye, what the human eye does is there's objects out there, and it'll focus those objects onto a screen, and the screen is the retina. So this is the front of your eye, basically the lens of your eye, and there's the screen, okay? Now, for the human eye, it's not that you move the screen back and forth, okay? The retina is kind of fixed. But instead, there's little muscles which make the lens, you know, thicker or thinner, and they change the focal point of the lens such that it, focuses onto the screen. Okay, so either you're going to move the screen back and forth until you get it in focus, or you're going to change the focal length of the lens until you get it in focus. And for most lenses that we make out of glass, you can't do that because the focal length is fixed. But for the human eye, the lens can actually change. You know, the muscles will actually pull out, and then it'll make the lens thinner, or they'll relax and they'll make the lens thicker like that, and then you can focus. For some of us, unfortunately, no matter how much the muscles pull or don't pull, they can't focus the image onto the back of the retina, and everything's blurry unless you wear glasses, and that's corrective lenses, okay? So I'm not going to do multiple lenses. You know, if you have several lenses, you could do that as well. But, you know, you can see how, you know, by changing the divergence just before you get to the focal, to the lens, you're effectively changing the focal length of the lens, okay? And so those are what corrective eyeglasses are all about. Okay, so let me give you some formulas for this. Okay, so below I first described the three rays, which I just described, but now I can give you some formulas. Okay, well, maybe I should just say something before I give you the formulas. How did the formulas come about? Because I'm not going to derive them. Again, they're not hard to derive, but I'm not doing that. You're not going to be physics majors. But how would you derive them? Well, take a look at this diagram. It's filled with triangles, isn't it? Okay, and so remember how similar triangles work? So if you form the ratio of the sides of two similar triangles, the ratios of those sides are the same. Okay, and so you've got a whole bunch of similar triangles. You've got, you know, like one triangle right here. See, there to the image. There's a triangle there, okay? There's one triangle. That triangle is similar to this triangle, okay? And that means there's a bunch of ratios in there, okay? So that's where these formulas come from, all right? So what are they? There's two of them that you need to know. There's this one, which is usually called the lenses formula, okay? And it basically relates the focal length to the distance of the image and the object from the lens, okay? So 1 over the focal length is equal to 1 over the distance of the object to the lens plus 1 over the distance of the image to the lens, okay? So basically the reciprocals add for the distances of the object and image, and that's got to equal the reciprocal of the focal length. Okay, there's equation number 1, pretty easy equation. Right? And here's equation number 2. It's basically a definition. It's a definition of M magnification. Okay, I didn't write that in here, but maybe I should have. M is called the magnification. Okay, and the magnification, what is that? It's like how much bigger is the object than the image, and it's basically like HI over HO, if you want to think of that, like how much bigger is the image than the object. But because of the similar triangles, it's actually equal to minus the distance of the image to the lens divided by distance of the object. Okay, and so this is known as the magnification. You can use either one of these to calculate it, all right? Usually use the first one, di over do, negative di over do, because di and do, they're coming out of the first equation, the lens equation, okay? Now, you'll notice there's a negative sign there, so signs are going to be important here, all right? So how do the signs work? Well, let me go back to the diagram. This is probably the easiest way to show you how the signs work. In this particular diagram, if DO is on the left-hand side of the diagram, then DO is positive. If DI is on the right-hand side of the diagram, then DI is positive. So in this case, both DO and DI are positive. Okay. HO is positive if the object is pointing up. You should always make the object point up, so HO should always be positive. But HI can be either positive or negative. HI is positive if the image is pointing up, but it's negative if it's pointing down. Take a look in here. It's pointing down, the arrow is pointing down, and therefore HI in this case is actually negative, all right? And so we'll see that when we do problems, but that's what this negative sign that's in there is all about, okay? All right. And for this particular case, again, this is the case where DO is bigger than F, we have the following signs. DO is positive, and DI is positive. So both DO and DI are positive. Okay, HO is positive. That's almost by convention. You should always point the arrow up. Okay, but HI, I just showed you that it was pointing down. And there's also a sign associated with the focal length. The focal length for a convex lens is always positive. Okay, so F is greater than 0. Okay, now the image can be characterized in 2 ways. All right. First is the orientation of the image, and this is actually coming out of HI. All right, so the image could either be inverted or it could be upright. All right, so if the image is inverted, the HI is less than 0. That's what is happening in this case. So in this case, the image was inverted. The other possibility, which you'll see in the next example, it's upright. The image will be upright. Okay, but there's something else, and this one's a little bit more subtle, and that's the type of image that's formed. And the 2 types of image that are formed can be either real or virtual. In this particular case, the image is called real. And what that means is that in order to see the image, you have to use a screen. In other words, the image is formed by rays converging onto a screen. If there's no screen there and the rays converge, they're converging on nothing, you won't see it. Okay, so a real image is formed by the rays converging onto a screen. Okay, the virtual, you'll see that one in a minute. All right, so you can actually get both of these out of this information up here. And if HI is negative, then the image is inverted. If HI is positive, then it's upright. Okay, so those are the 2 possible orientations. HI is positive, it's upright. HI is negative, it's inverted. Okay, the real and the virtual images, that actually comes out of DI. If DI is positive, then the image is formed by converging rays on the opposite side of the lens. And you'll see in a minute, if DI is negative, the image is formed because rays are diverging from behind the lens. Okay, so if that's a little bit abstract, hold on, you'll see my next ray diagram. Okay, all right, so what we just did was we looked at the case where DO was bigger than F. Let's now look at when DO is smaller than F. Okay, so we're going to put the object closer to the lens than the focal point. And here's what your ray diagram now looks like. All right, so what we have here, here's the lens. And I move the focal points out a little bit further to make this diagram a little bit better. So here's one focal point right there. And I didn't label it F, but that dot there is a focal point. And here's another focal point there. The fact that the image is right beside the focal point was a little bit of a coincidence, but you know, it's not right on it actually. So there's a focal point there and a focal point there. Okay, and here's my object. So notice that the object is now closer to the lens than the focal point. All right, and let's trace the rays that are coming from this object. So we've got 3 rays that we can trace, but we're only going to trace 2 of them. And in this case, it's ray 1 and 3, which are the easy ones to trace. So we'll only trace those 2. So we'll remember what the rule was for ray 1. The ray travels parallel to the axis until it hits the lens. Then it bends and goes through the focal point. So here it is, right here. So here's the ray. It's traveling parallel. It impinges on the lens, and it bends such that it passes through the focal point. Okay, there's ray number 1. Ray number 2 we'll ignore. Ray number 3, a ray which leaves the tip of the object, passes through the middle of the lens, doesn't get bent at all. So there's ray number 3. Okay, so never mind these dashed lines here of the image. Just ignore that for a second. Here's the object. Here's ray 1. And here's ray 3. Okay. If you take a look at ray 1 and ray 3, even though this is a converging lens, in other words, it tends to bring the rays together, notice that ray 1 and ray 3, they're actually divergent from one another. Okay? So they'll never come together onto a screen and form an image onto a screen. All right, I'll go back to that other diagram to contrast it in a second. Here, ray 1 and ray 3, they will never meet. And even if you drew ray 2, which I don't want to go through the rules of drawing ray 2, but ray 2, you would start from this focal point, it would go up to here, to there, and then it would go up parallel like that. It would also diverge. Neither is ray 1, 2, or 3 will never come together on the right-hand side of the lens. Okay, so the image is not formed on the right-hand side of the lens. All right, where's the image formed? Well, imagine that you have a human eye here, and the human eye is looking through the lens behind it. It wouldn't see the object directly. It would see the object, but with its rays bent by the lens. And so it looks like ray 3, if as far as the eye is concerned, it looks like ray 3 is coming from, keep going back, keep going back. That's what my dashed lines are. Dash, 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 for somewhere back here. Okay? So ray 3 seems to be coming from back there like that. Ray 1, if you just draw it back, it seems to be coming from here. Dash, 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 dash there. And these 2 dashed lines, that's where ray 1 seems to be coming from and where ray 3 seems to be coming from. They both seem to be coming from this point right there. That's where the image is formed. Okay? So the image is actually formed on the same size of the lens as the object, right there. And where those 2 meet, that's the tip of the image. Okay? So again, the object is emitting these rays. These rays are diverging. The eye sees the diverging rays, but they seem to be diverging from this image back here. Okay? And so in this case, you have a very different kind of image. It's not an image formed because the rays are converging together onto a screen. Rather, your eye sees rays that are diverging. They appear to be diverging from an image which is on the same side of the lens as the object. Okay? So I'm going to contrast. I'm going to go back to that other diagram in just a second, but just keep this in mind. Okay? See 1 and 3, they're diverging. Never will they meet. And even if I drew ray 2 in there, okay, so ray 2 is a little hard to draw because you see, how does ray 2 work? Well, first you pass through the focal point, but then it goes off to infinity. You go, well, that's kind of silly. So ray 2 is kind of useless, but not quite. You can pass the ray backwards. So it starts at the focal point, passes through the tip, gets to the tip of the air, gets to the lens there, and then goes out parallel. Okay, and so you'd have ray 2 up here, ray 1 there, and ray 3 there. And if you were to project ray 2 back like this, so ray 2 would be somewhere like that. Project ray 2 backward there, it also would seem to come from there. Okay, so all of the rays seem to be diverging from an image on the same side of the lens as the object. Okay, so they're all diverging on this other side, even though it's a converging lens. Okay, and take a look at how that's different than this. Okay, see these rays? They're not diverging on the other side of the lens. They're converging, and they're converged where the image is formed, and you have to put a screen there to see it. That's a real image. That's called a real image. And this one is called a virtual image. Okay? And in this case, it turns out that the image is erect, or upright. Use either words, okay? So it's upright. It's pointing up. And also, notice that the image is on the same side of the object as same side of the lens as the object, okay? And so in this case, DO is positive, but DI will turn out to be negative, okay? And so when DI is negative, you know it's a virtual image. And when HI is positive, you know that it's upright, okay? So you heard me say erect a minute ago. You can either say upright or erect, whichever. Okay, so it's either inverted or upright or erect, okay? All right, so in this case, we have the situation where DO is positive. We should always have DO positive by convention. DI is negative. That tells you the image is virtual. HO is positive. That should be so by convention, okay? And HI is positive, which means that it's upright. So you can conclude from this that the image is both upright and virtual, okay? Whereas in the previous situation, the image was inverted and real, all right? All right, so this was the situation with the convex lens, okay? And the next one we're going to study, the last one we're going to study is the concave lens, okay? So for the concave lens, let me see if I can get, yeah, good. Just scroll up a bit more. There we go, okay? So here's a concave lens, all right? And wait, one more. There we go, all right. So here's the symbol for a concave lens, all right? So again, you could draw a lens which is kind of bent in the middle like that, all right? I didn't draw a concave lens, but concave is thinner in the middle and thicker at the end points, all right? So you can either draw that, or this is the symbol for it. You just got this kind of line there, and then you've got these inverted arrows at the top and bottom, okay? Just symbolically like that, all right? You still have the axis to the lens there like that, all right? And we're going to have an object here like this. All right, and it doesn't matter whether the object is closer to the lens or further from the lens than the focal point. It doesn't work like that with the concave lenses. You've got just one possible situation. Okay, and so I've got f1 here and f2 there, but they're both the same distance f from the lens. So the distance from f2 to the lens and this from f1 to the lens is still the same. Okay, now here's the object right there. All right, so there's the object. Ignore the image if you can for a minute. Okay, so here's the object. What rays are we going to trace? Well, we'll trace 1 and 3 again. So 3 is the easy one because 3 is, leaves the tip, passes through the middle, and doesn't bend at all. There it is. Okay, so there's ray number 3. Ray number 1, what does it do? Ray number 1 travels parallel, hits the lens, and wait, what does it do for a concave? For a convex, it bends and passes through the focal point there like that. But for a concave, it bends and diverges away from this focal point f1. So when it gets here, you see that dashed line there to f1? To that point right there? The ray bends away from f1. So there it is right there like that. So the rule is a little bit different. It doesn't bend and pass through f2. Rather, it bends such that it's traveling away from f1. Okay? So this dashed line in there, traveling out there like that, is straight. That's how concave lenses work. All right, so the rule for ray number 1 is a little bit different. All right, and there's also a rule for number 2, but I don't have to give it to you because it's sufficient to do just two rays to see where the image is formed. Once again, ray 1 and 3, they'll never converge, so you'll never get a real image. You could move the object back and forth. It doesn't matter if it's out here further from the focal point or close to the focal point. No matter where the image is on the other side of the lens, these rays are going to diverge, okay? So you know that if these rays are diverging once they pass through the lens, once again you have a virtual image, and the virtual image is formed by where the rays appear to be coming from. Ray 3 appears to be coming from along this line. Ray 1 appears to be coming from, follow the dashed line here, where do the two rays meet? Right there, okay? And so the image is formed right there, all right? So here's the object, and there's the image. All right, again, it's a virtual image, and it's upright, okay? Well, in this case, the image is made smaller than the object, okay? This is a demagnifying glass, all right? And in the previous case, this one, the image was bigger than the object. This is a magnifying glass, okay? So a magnifying glass only works if you put the object closer to the lens than the focal point. And you could try this if you've got, I'm sure you've got a magnifying glass at home. Just put it in front of like your finger or something, and you move it back and forth, and you'll see that, you know, as you move the lens back and forth, it definitely, the image will look bigger. Your finger will look bigger as you look through it through the magnifying glass. But if you pull it too far, such that the object is further away than the focal point, well, then it becomes a blur, and you'll see that it just turns into a blur. Okay, so convex lenses, where the object is closer to the lens than the focal point, act like magnifying glasses. And concave lenses, doesn't matter where you put the object, they're always demagnifying lenses. Okay, so there you go. All right, so that's all the theory. And at this point, and this is just a repeat of the numbers we had before. And at this point, we can do problems, okay? Just one more thing I need to mention. The focal point for a concave lens, it's negative. It's always negative. All right, let's do a problem, and then we'll be done, okay? So here's an example. A convex lens has a focal length of 10 centimeters. We place an object 15 centimeters from the lens, and we want to know, where is the image formed? Probably a better way to say that is, how far is the image formed from the lens? So where's the image formed? Is the image inverted or upright? Is the image real or virtual? And what is the magnification? Okay? All right, so let's do that. Well, we're going to use this lens formula here. 1 over f is equal to 1 over do plus 1 over di. Okay? And the focal length for a convex lens is positive, so it's positive 10 centimeters. Okay? And the distance from the object to the lens, I told you, is 15 centimeters, and that's positive by convention. All right? And so if you just take this and we're solving for di, where is the image? So just isolate the di. That's going to equal 1 over f minus 1 over do. And so that's 1 over 10 minus 1 over 15. All right? And I also say there, look, you know, you don't have to convert to meters, because if you plug in centimeters here, you're going to get out in centimeters. Okay? And just plugging this through on your calculator, turns out that di is going to be positive 30 centimeters. The fact that that's positive means that the image is on the opposite side of the lens of the object compared to the object. Okay, so this is like our first case. All right, and the image is opposite side of the lens, so the image must be real, and meaning that it's formed by converging rays. All right, the magnification is going to be given by this formula. All right, well, you have negative, di is positive 30, do is positive 15, so it's negative 30 over 15. That gives you negative 2. That means if HO is positive, that HI must be negative. Okay, so when you get a negative magnification there, the fact that this is negative 2 tells you that HI must be negative. In other words, the image is inverted. All right, so in the magnification, the sign tells you whether it's inverted or not. And the number, in other words, just the absolute value, tells you that the image is actually twice the size of the object. Okay, so it's twice the size, but it's inverted. Okay, it's upside down. All right, that answers that first question. And now I said repeat this problem, but this time assume that the lens is concave. All right, and for a concave lens, it still has a focal length of 10 centimeters, but we have to put negative, because the focal length is always negative for concave lenses. All right, so where is the image formed? Well, you know, same formula, and just isolate di, 1 over di there. So that's 1 over f minus 1 over do. And everything's negative here, so it turns out that if you just work this through, di turns out to be negative 6 centimeters. All right, so the fact that di is negative tells you that the image is on the same size of the lens as the object, and that means that it's virtual. All right, so di negative means that we've got a virtual image. All right, now if we plug the numbers in to our magnification formula here, be careful with the signs, because we've got two negatives going on here. This negative is because it's part of the formula, but di itself is negative, and so it's negative 6, so you have negative 6, which is positive. Okay, so you get 6 divided by 15, which is 0.4. That's positive. Okay, so the fact that the magnification is positive means that HI has to be positive, means that the image has to be upright. All right, now it's 0.4, which means that it's only 40% the size. The image is only 40% of the size of the object, so it's been demagnified, but it's still upright. Okay, so this last one is exactly this situation right here. Okay, so the second example was the situation there. The first example was the situation right there. Okay? So that's it for the lecture on optics, and that's it for the course. There's going to be no new material. Again, I'm going to still be doing lectures as we go on, but there'll be live streams in which you can interact with me, and all I'll be doing is solving problems. And watch your emails, because I'll tell you on the day what kind of problems I'm going to be doing. All right, thank you.